Hey guys, this is section 5.4. We're going to look at kind of a cool theorem, I think. So what we've been doing up until now is figuring out probabilities of events happening based on populations that are normally distributed. So by way of review, you take this population, here it is, and you take these data points out of them. So if we're measuring, like, let's say people's blood pressure or height or something, all of those dots represent one person. And you come over here, you calculate their blood pressure, their height, whatever you're measuring, and you start plotting their data points. And what we've seen up until now is that the further away, if this is your population mean, the further away you get from the mean, the less and less points there are. And so as you plot these individual points, you create what we call this normal distribution, which we've been drawing like this up until now. So what I really want you to understand is these are individual data points that are being plotted, and then we're calculating the probability based on that. Now, the question is, this is a very specific population in that these population points plot into a normal distribution. Sometimes that doesn't happen. So what if we have a population right here and we go and we plot all our individual data points? We come over here and we get some funny little distribution like this. Now what? That's not a normal distribution. And our calculator can't handle that problem because all of the numbers in the calculator are based on a normal distribution. So what do? I'm glad you asked. What we do with this population is, instead of looking at individual data points, we take a sample. So here's one sample. We randomly choose it. So it's, well chosen, random, and equitable, all that stuff. And we calculate the mean of this sample. So I'm going to call that X bar 1. So remember, X bar is the notation for a sample mean. So we're taking, like, let's say we're measuring heights. We're taking a sample of people, we're calculating all their heights, and we're calculating the mean of that sample. And then we're going to take that data value and we're going to plot it. Okay. Then we're going to take another sample out of the data. We're going to call this X bar 2. That's going to be a second sample mean. We're going to plot that. Then we're going to take another sample mean, X bar 3, and we're going to plot that. Okay, you get the idea. And what we're going to do is we're going to take that population and we are going to pull all the possible combinations of samples out of that population. And when we do that, what we find is those sample means end up being normally distributed. Now that's pretty amazing, especially since the population distribution looks like this. This is the distribution of sample means. Now, what I want you to understand here is each of these dots represents a mean of a sample, not one individual data point, okay? So you can't go in here and take this one value right here and say that represents a person's height. It does not. It represents the mean of a sample of people's heights, all right? But what that allows us to do is take some kind of wonky population distribution and approximate it as a normal distribution, and then do our regular problems on it. So your problems in 5.4 are going to look really similar to 5.2. So the CLT, the central limit theorem, we call it, or the CLT, says that a distribution of sample means is normal if one of two things happens. First, if n is bigger than or equal to 30. So this is interesting. So as you take this population that we talked about and you go, oh, my population's not normal, so I'm going to take these samples, all of these X bar 1s and X bar 2s, X bar 3s. As you're taking those, you have to pull samples bigger than or equal to 30 in order for this distribution of sample means to become normal. So the we always talk about the size of your sample, that really matters. And in this case, it matters. And there's an exact number where we have to hit at least 30 or above. Okay. So either that needs to happen, or your population has to be normal. And if one of those two things happens, then you can take these sample means and you can use that distribution to approximate your probabilities. Okay, so let's look at a picture of this, these two scenarios, so that you've got that in your brain. So here we go. Scenario one. Here's any population distribution. It's not normal. Okay, but if we take samples bigger than or equal to 30, and we plot those sample means, then we get a graph shaped like that. Okay. Or if your population is normal to begin with, then you can take samples of any size. It doesn't matter. You can take sample sizes of 2, 3, 4. It doesn't matter how big they are. They will still be normal. Now, that does change the distribution a little bit, though. Look at this picture. The difference between these guys. The top one is wider than the bottom one. So what happens when your population is normal and you start pulling sample means from it is that it tightens up the standard deviation. The data becomes less spread out. Why? Because we're plotting averages. So the averages tighten in towards the population average, right? That's the idea. Okay, they're pulling in, so the standard deviation is getting less. And we have a formula for it. The standard deviation. Now, what we do is we say sigma x bar. So what that means is it's the standard deviation of the sample means. That's this situation. Why do we use x bar? Because that's the notation for the sample mean. So the standard deviation of the sample mean is calculated by taking the original population standard deviation and dividing it by the square root of the sample size, whatever you chose. Okay, and that's how you're going to calculate your new standard deviation. Now look at the means on these two problems. They're not different. Here, this is my population mean. This is also my population mean. The curve didn't shift at all. It just tightened itself up. Okay, so as you're doing problems using the central limit theorem, you're going to need to recalculate your standard deviation. All right, let's take a look at a sample problem. And we'll go through exactly what to do in a problem. So first of all, the weights of ice cream cartons produced or manufactured are normally distributed with a mean weight of 10 ounces. Okay, so let's draw a picture of that. I've got a normal distribution. I've got a mean of 10 ounces. That's my population mean. And I've got a standard deviation of 0.5. So that means that this one standard deviation in either direction, 10.5, 9.5. All right, that's our distribution. Now, the first question says, what is the probability that a random selected carton has a weight greater than 10.21 ounces? This is a 5-2 problem. You've done these before. I want you to notice a key word here. It's saying, what is the probability that a random selected carton? This is how you know that it's 5-2 problem, because remember our picture, here's our population, right? And we're plotting in 5-2, we're looking at all the individual data points. So when I talk to you about a data point, I'm talking about a single milk carton or ice cream carton in this case. Okay. And that's how you know it's a 5-2 problem. We have not done anything with sample means. We're just looking at a specific thing, a specific person. It's always one of them. Okay. So let's go through this by way of review. 10, I want to know what's the probability that a random selected carton is greater than 10.2. So 10.21 is like right here, let's say, and greater than is to the right. Okay, so I'm going to go on my calculator. I'm going to do, go to my graphing section. On your TI, you're going second distribution, inverse CDF. On this guy, I'm going to go stat distribution plot, I'm going to do a normal distribution. My mean is 10. My standard deviation is 0.5. Okay, you can look at that picture. That's that guy. And then I want a CDF. So CDF, that's the whole picture is colored in, but I don't want that. I want 10.25 or 21 on up to the top. Okay, so what's that probability? That's going to be 0.337. So we can say that there is a 0.337 or almost 34% chance that you randomly select a carton that weighs greater than 10.21. Okay, that's 5-2. Now look at part B. You randomly select 25 cartons. That's the key. This is a central limit theorem problem. Why? Because in this situation, we're pulling a sample. That means we're going to use the central limit theorem. Okay, there's another clue that you're in a 5-4 problem with central limit theorem is when it asks about the probability right here, which both of them do, they both ask for a probability, but what you're asking for a probability of is the mean weight. So that's your X bar 1, X bar 2, like what now we're plotting sample means instead of individual data points. All right, so let's draw a picture of this. I've got my distribution. It is still normal, okay? And my mean is still 10. But now because I'm looking at sample means, I have a different standard deviation. So the first thing that you're going to do is the first thing that you need to do is tell me why you can use the central limit theorem, because we are going to use the central limit theorem. Okay. So I'm going to say the CLT applies because, and the because is going to be one of two things. It's your two qualifications that we wrote down. Either I pulled a sample bigger than or equal to 30. So either you're going to say because n is greater than or equal to 30, or because your population is normally distributed. This first sentence will always say the same thing, one of those two, okay? CLT apply because n greater than or 30 equal to 30, or the population is normal. So let's look at our problem. Well, our n is 25. Our sample's 25, so it's not bigger than or equal to 30. But look at what it says up here. These cartons are normally distributed. Okay, so that's our reason. So CLT applies because the population is normal. That's going to be your first step on all CLT problems. Your second step is to recalculate your standard deviation because it's different now. So I'm now looking at my standard deviation for my sample means. Now, what about the mean? The mean stays the same. Remember, the population mean is equal to the sample mean. Okay, so that doesn't need to be recalculated, but this one does. Our formula is sigma over the square root of n. And in this case, our sigma, our standard deviation of the population is 0.5, and our n is going to be 25. Okay, so when you divide those out, you get 0.1. So our new standard deviation is 0.1. That means my picture changes a little bit. This now becomes 10.1, and this becomes 9.9. Instead of the 0.5 spread. So you can see by the numbers, this is shrinking in, right? I mean, I didn't draw it to scale, but now it's tighter because I'm only spanning out 0.1 instead of 0.5. Okay, and then the question is the same for this. It's what's the probability that the mean weight is greater than, I wrote all this and we can't see, greater than 10.21 ounces. So I'm still doing 10.21, but because I'm on my sample means and my drawing is, the scale's a little bit different, like it's shrunk in because of the standard deviation. Now look at where 10.21 is. It's way out here, right? Because that's going to be 10.1 and then 10.2, 10.21. That might be a little far. Let's scoot it in. Oh my gosh. Let's scooch it in just a little bit. Like, I don't know, maybe it's right here. Okay, doesn't matter, but greater than or equal to 10.21. Here we go. Okay, so as you can see, what you'd expect, look at the difference between these graphs. What you're going to expect is the probability is going to be smaller, right? Because 10.21 now is more up into the tail because this thing shrunk down. Okay, so let's go and do and then the calculator part of this is exactly the same as what you were doing. On a TI, you're going to do second and then distribution. You're going to do that inverse norm option, and you're going to enter your lower and upper bounds. On class calc, we're going over here, and instead of 0.5 for my standard deviation, I'm using 0.1. See how that shrinks this? Whoop, sorry. See how that shrinks the colored part right there? Okay, 10.1 on up. Now look at the probability, 0.01, let's call it 0.018. Okay. So my answer to this is going to be 0.018. All right, and that's the difference between the CLT. Now, most problems are going to be straight up CLT problems on this section. They're always going to be pulling sample means. Some of them have a part A and B, like you saw here, where one is a 5.2 problem, one's a 5.4 problem. The goal is to get you to identify the difference between the two, because on the test, everything's mixed up. Okay, so pay attention to the language. Again, you're looking for, are we taking a selected item, one item, or are we taking a sample and we're looking for the probability of a mean? That's going to be the difference there. All right, thanks for tuning in. I will see you next time.